YouTube.
Okay.
Now let me check.
All right.
And then it says perhaps in 2 to 4 minutes. Exactly. We'll know if it was 2 or 4 minutes.
All right. Robert, we all good? Okay. Hi everyone, welcome to the Geotalks. I shouldn't say at 4 p.m. on a Thursday. It feels like it should always be 4 p.m. on a Thursday, but it's not. Thank you for joining us in a slightly larger venue, which should tell you that we were expecting this to be a popular talk, which it looks like it is. So welcome to everyone here and on YouTube. I'm not going to do the introduction, but I want to introduce Dr. Tebogo Makobela from Department of Geology at UJ, who very kindly offered for Peter to give the talk here at Wits, which is lovely, and we're very appreciative. Tebogo, so thank you, and I'll ask Tebogo to introduce Peter right now. Over to you guys.
Thank you, Grant. Good afternoon, everyone. Well, I must say it gives me great pleasure to introduce Peter because I think he is a very easy person to introduce. But let me first tell you that, the first time I met him, I called him Pieter, and I think you know why. Because if you look at the spelling of his name and you are from South Africa, it makes sense, right? And then I learned that it's actually Pieter Vermeesch, and he is from the University College London, UCL in London. But he is born and raised in Belgium, went to Ghent, University of Ghent, and then he made his way to London, but he's been a few places. By expertise, he's a geochronologist, and you would be doing him a great injustice if you try to box him into a specific methodology, because I have learned over the years that Peter loves all geochronological methods. My introduction to him was a program called CosmoCalc, which was a data reduction software for cosmogenic techniques, burial ages and erosion rates. And I thought, oh, this guy does cosmogenic nuclides. But then, many of you probably know him for isoplot R, which we use for calculating geochronological ages and rates across different methods. And so Peter's interests are geochronology, but he's interested in other geomorphic processes, but more importantly, statistical modeling as applied in geology and geochemistry, as well as geochronology. And the work he's going to present today is as a result of the statistical, parameters involved in uranium-led geochronology, because that technique is extremely important for determining ages of fossils out in the cradle of humankind especially. And we've always known that many of the important fossil finds in the cradle are dated to about 2 million years. But Peter thinks they are a different age. And my name is up there because he has convinced me that we've underestimated many of the ages. And so we've got a lot of work that is up and coming, and he's going to present some of that. Peter, over to you.
Thank you very much, Tebogo, for this very kind introduction. Thank you, everybody, for being here and online. So my name is Pieter Vermeesch. I'm a geochronologist at UCL, and I'm a little bit nervous presenting on paleoanthropology in a room that contains undoubtedly many people who know a lot more about the subject than I do. So I hope that you'll learn something, maybe something useful out of my presentation, and I look forward to learning from you after the presentation. So what got me interested in paleoanthropology? Well, the field of paleoanthropology, one might argue, started off with the publication of this famous book, The Descent of Man, by Charles Darwin in 1871. In this book, Darwin proposed that humans were related, or closest cousins in the animal kingdom are the great apes of Africa and of Asia: gorilla, chimpanzee, gibbon, orangutan. Darwin himself favored an African origin for the human species, but many of his contemporaries favored an Asian origin. And their case was kind of bolstered by the discovery in the late 19th and early 20th century of Homo erectus fossils in Indonesia and in China. It wasn't until more than 100 years ago, until about 100 years ago in 1925, that the first more ancient hominin fossil was found here in South Africa by anatomist Raymond Dart. So this fossil, which was morphologically clearly older than Homo erectus, was baptized a town child, and it actually took 20 years before the paleoanthropological community agreed that this was indeed an ancient human and not some extinct baboon. But when that consensus was reached, that essentially settled the debate between the out of Africa and out of Asia hypotheses. So the town child is one of the most important fossils ever to have been discovered. Yet, more than 100 years after its discovery, we still don't know exactly how old it is. And that's what got me interested in this problem. After the town child, many other Australopithecines, early hominins, were found in Africa, both in southern Africa and in eastern Africa, including the famous Lucy, which is a nearly complete skeleton of Australopithecus africanus. The East African fossils are relatively easy to date using potassium argon or argon-argon dating of volcanic ash layers, which are abundant in East Africa because the sites are located in the East African Rift, which has abundant volcanism. Now, no active volcanism exists or occurs south of Tanzania, and therefore there are no ash layers and no easy way to date the Southern African and Western African fossils outside the East African Rift. In fact, for many years, these fossils were deemed to be undateable. But then about 20 years ago, two methodological breakthroughs occurred that allowed geochronologists to finally pin down the ages or constrain the ages of these Southern African fossils. The first of these methodological breakthroughs was the development of cosmogenic nuclide burial dating, which indicated that the famous fossils of the Sterkfontein cave system in South Africa were about 4 million years old, which is similar to Lucy and the East African Australopithecines. 3 years later, another technique, uranium-lead dating of carbonates, was applied to the same cave systems in Sterkfontein, and to the researchers' surprise, those ages disagreed with the cosmogenic nuclide dates, not by a little, but by a lot. The uranium-lead dates are only about 2 million years old, so half the ages obtained by cosmogenic nuclide dating. This is a big disagreement, and as you can imagine, a vivid argument ensued between these two camps, where the cosmogenic nuclide people kind of raised objections against some of the methodologies and sampling strategies for the uranium-lead people, and vice versa. All right, so in order to try and resolve this disagreement, I'll have to go into quite advanced geochronology, and I appreciate that not everybody in this room may be an expert in geochronology, so just let's put everybody on the same page and start with a basic introduction to geochronology, on which I will then build to do the more advanced stuff later on. I apologize to those of you who are experts in geochronology. You can go to sleep now. I'll wake you up when we get to the advanced geochronology. So geochronology is the science and the art of dating rocks, and there are many different tools in the geochronological toolbox that are all based on essentially the radioactive decay of isotopes of carbon, uranium, potassium, rubidium, and so forth. These different tools all target different parts of the geologic timescale and different minerals, different materials. When you're interested in relatively young processes, up to 50,000 years, say, then it's relatively easy, straightforward to obtain a date using radiocarbon, which is a short-lived isotope of carbon with a half-life of 5,730 years. Old rocks, more than 5 million years and up to 4.5 billion years old, are also relatively easy to date using the long-lived isotopes of uranium, potassium, rubidium, which have half-lives of hundreds of millions to billions of years. These isotopes are survivors from the formation of the solar system and the supernova that preceded it. Unfortunately, the period in between these two end members, so timescales between 50,000 and 5 million years are much harder to date. And this dating gap covers time spans that are too old for the short-lived isotopes and too young for the long-lived isotopes. It's very unfortunate that they are so hard to date because this is a very important period of time. That's where quaternary glaciations happened. That's where human evolution happened. So a lot of effort has gone into trying to bridge this gap. And so there are 3 techniques that are used to plug this gap that are relevant to human evolution. The first of this I already mentioned is potassium-argon dating. It's based on the radioactive decay of a rare isotope of potassium, which is a major element in the Earth's crust, to argon, which is a major constituent of the atmosphere with a half-life of 1.25 billion years. So this is a very slowly decaying nuclide, but because our machines are so sensitive, it still allows us to date processes that are occurring over tens to hundreds of thousands of years. So, argon in potassium-bearing minerals has 2 sources, atmospheric argon and radiogenic argon. In order to disentangle these 2 sources of argon, we need to analyze at least 2 aliquots, 2 splits of the same sample. Suppose that we've got a volcano that erupts and spews out these ash layers containing minerals, and suppose that we separate 2 minerals, olivine, which does not contain potassium, and feldspar, which does contain potassium. Then initially, when the ash layer has just settled down, the argon composition, the ratio of argon 40 to argon 36, and these two minerals will be exactly the same. As time progresses, the olivine isotopic composition will not change because there's no potassium, but the feldspar will gain additional argon 40 due to the decay of potassium 40. Lines connecting the olivine to the feldspar in this isotopic ratio space will increase in slope, and that allows us to calculate the age of the feldspar. So this diagram and these lines are called isochrons, and this is the conventional way of plotting them. There is another way to plot them in which we don't put argon 36 in the common denominator, but we use argon 40. This is just a permutation of the isotopes. The same information content can be presented in a different way, in which the isochrons, the lines connecting the 2 minerals, are not positively sloped but negatively sloped, showing a mixing between an inherited and a radiogenic end member which marks the horizontal intercept of those lines. I'm showing this in some detail because we will see many of these diagrams later in my presentation. Right, so we can date ash layers below and above a fossil, and that allows us to constrain the ages of Eastern African fossils. Cosmogenic nuclide dating is a second method that can be used to date hominins. It is based on the production of rare isotopes of aluminium, aluminium-26, and beryllium, beryllium-10, by nuclear reactions with cosmic radiation. The Earth is constantly bombarded by cosmic rays produced by the galaxy around us. Most of these cosmic rays are deflected by the magnetic field or filtered out by the atmosphere. A tiny fraction of the cosmic radiation reaches the surface of the Earth. And when these cosmic ray neutrons, most of the time, hit target atoms of silicon and oxygen in rocks and soils in the uppermost 1 to 2 meters of the Earth's surface, they produce these nuclear reactions, producing small but measurable concentrations of aluminium-26 and beryllium-10. Now, when the landscape erodes, it produces sand that gets washed into rivers. That sand will inherit the aluminium-26 and beryllium-10 signal from the landscape. The sand travels down the river and it may be washed into a cave where it will be blocked from cosmic radiation. So the production of aluminium-26 and beryllium-10 ceases. Their radioactive decay, however, continues. We can then use the relative and absolute amounts of aluminium-26 and beryllium-10 in those cave sediments to constrain how long ago the sediment was washed into the cave. If there is a fossil inside those sediments, you can then estimate the age from that. And then the third method that is relevant to today's talk is the uranium-lead method, which, as the name suggests, is associated with the radioactive decay of 2 isotopes of uranium, 238 and 235, to 2 isotopes of lead, 206 and 207. These 2 isotopes of uranium have a constant ratio in the solar system, giving us 2 clocks for the price of 1, and 2 isochron plots for the price of 1. So we can calculate a uranium-238 led to a 6H, or we can calculate a uranium-235 led to a 7H. If those two H's agree, we have an internal quality control that gives us great confidence in the uranium lead age. That quality control is absent from most other chronometers, making uranium lead a particularly powerful chronometer. An alternative way to combine these two methods is to substitute lead-204, which is the non-radiogenic isotope of lead, for lead-207, and that produces again these mixing lines, these inverse isochrons, connecting a non-radiogenic end-member composition with a radiogenic end-member composition. The only difference between this diagram and that one is that the radiogenic end-member doesn't end on the horizontal axis, but it ends on this red line, which is called the Concordia line. And here is an overview of some key dates for those three methods for Australopithecines in Eastern Africa. These are potassium-argon and argon-argon dates. And Southern Africa, using cosmogenic nuclides and uranium-238 to lead-206, which is the more precise method due to the higher abundance of uranium-238 relative to uranium-235. Again, the cosmogenic dates agree very well with the Eastern African potassium-argon dates, but the uranium-lead dates do not. To resolve that difference, or at least explore a possible cause for that difference, we now need to go to more advanced geochronology, so the geochronologists can wake up, because now I'm going to go into the nitty-gritty of speleothem uranium-lead dating. My earlier introduction to the uranium-lead method was oversimplified. I kind of pretended that uranium decays straight to lead, whereas in reality there are many intermediate nuclides, 13 steps of radioactive decay that uranium-238 encounters on its way to becoming lead-206. These intermediate daughters are all much shorter lived. They have much shorter half-lives than uranium-238. The immediate daughter of uranium-238 is thorium-234. It has a half-life of not 4.5 billion years, but only 24 days. This is a very radioactive isotope of thorium-234. At any given time, there are hardly any atoms of thorium-234 in a speleothem or in any mineral on Earth. However, this tiny amount of thorium-234 is so radioactive that the radioactivity produced by the thorium-234 is the same as the total radioactivity produced by the billions of atoms of uranium-238. This is called secular equilibrium, and given enough time, any collection of uranium atoms decaying to lead will develop this secular equilibrium. If the secular equilibrium had been established at the time of formation of our rock of interest, then we can mathematically just ignore all the intermediate daughters, and we can just take the ratio of lead to uranium in this simple age equation to estimate the uranium-lead age of our sample. And this is the equation that is used in most geochronological applications for igneous and metamorphic rocks. However, in carbonates, we can't use this equation. And that is because young carbonates are often, nearly always, disrupted relative to secular equilibrium. There are two disruptions that are particularly important associated with the two longest-lived intermediate daughters. Thorium-230 is nearly always depleted relative to secular equilibrium in young carbonates because thorium is insoluble in water, unlike uranium. If this thorium-230 bucket is empty when the carbonate first formed, then we will end up underestimating the uranium-lead age. In contrast, the uranium-234 bucket tends to be overfilled relative to secular equilibrium. This is a little bit harder to explain than the deficit of thorium-230. There is not a chemical reason for the 234 enrichment. It has a mostly physical reason. It relates to the fact that uranium-234 is enriched in river waters because it is preferentially leached out of weathering rocks in the hinterland and the catchment areas of the waters that feed caves, due to the fact that uranium-238 decays, producing an alpha recoil that weakens the sites in which the uranium-234 sites. Anyway, whatever the reasons may be, uranium-234 is often enriched relative to uranium-238 compared to secular equilibrium. Any initial excess of uranium-234, if you don't account for it, ends up producing overestimated uranium-lead ages. Now, given enough time, a few million years, this initial disequilibrium will fade away, will disappear, and secular equilibrium will restore itself, removing all evidence for that disequilibrium. The problem with the cradle of humankind is that it is one of the, maybe the worst place in the world to do carbonate uranium-lead dating, because it has the highest enrichments of uranium-234 relative to uranium-238. So it is modern drip waters in southern African caves and these dolomitic areas of the cradle of humankind have 234-238 activity ratios of up to 9. And recent cave sediments, when you extrapolate back to the time of formation, indicate that the activity ratios can go up to 12. It's a very interesting physiochemical question how that can happen, but it happens. We can measure it, and it's causing problems. Because given enough time, 1-2 million years, that initial disequilibrium between 234 and 238, and between 230 thorium and 234, it will disappear. It will fade away, and the evidence for it will be lost. And that is shown by these red arrows on this diagram that shows how the activity ratios change through time, moving to secular equilibrium, activity ratios of 1, marked by this star. So in the next few slides of my presentation, I will show you how you can calculate these lines, because we will use them to undo the damage done by disequilibrium and correct our uranium-lead ages for it, provided that the rocks are not too old. All right, let's go into the nitty-gritty. This is a system of coupled differential equations that describes the evolution of all these intermediate daughters through time. It was first described by Ernest Rutherford, Nobel Prize-winning physicist in the early 20th century. It shows that the rate of decay, the number of decay events that a Geiger counter would measure, of uranium-238 is negatively proportional to the amount of uranium-238. The rate of decay, the rate of change of the uranium-234 content of our sample is negatively proportional to the number of atoms of uranium-234 and positively proportional to the number of uranium-238 atoms, because uranium-234 is made by the radioactive decay of uranium-238. Any atom of 238 that is lost is a uranium-234 atom gained. So the system of differential equations was solved by this man here, Harry Bateman, in 1908. That paper is no longer under copyright, so you can download it free of charge. I warmly recommend that you do so. It's amazing. It has these extremely long equations that were all derived by hand. These early 20th century physicists were extremely good mathematicians. And there's no mistakes in the paper. It's remarkable. But it is unwieldy and a bit messy to present. So I prefer an alternative formulation that was brought to the attention of the geological and geochemical community by Francis Albarere, French geochemist in the 1990s, that recast this system of differential equations into a matrix form, nice and clean. And that formulation was independently developed and extended to include lead by my colleague and co-author Noah McLean. Noah and Francis showed that the solution to this matrix derivative equation or differential equation is a so-called matrix exponential. It's a function that allows us to predict from any given initial conditions, initial amounts of uranium-238, 234, etc., for any amount of time, t, what the present-day relative amounts of uranium-238, 234, and lead-206 would be. It's a forward modeling tool. An interesting result is obtained if you replace t with infinity. After an infinite amount of time, as I explained, we move to secular equilibrium. Well, you can use this equation to show that the ratio of the radioactivities of uranium-234 and uranium-238 in secular equilibrium is not 1. So the number you read in textbooks is wrong. It's not 1, it's 1.000055. This seems very counterintuitive, but actually makes sense. It reflects the fact that 0.00055% of the uranium-238 has decayed during one half-life of uranium-234. I think it's quite interesting. All right, we can use this matrix exponential to draw the lines on this curve, on this diagram, and we can use it to assess how much damage initial disequilibrium can do when you don't correct for it. So suppose we've got a hypothetical speleothem that is 5 million years old and has this ridiculous 12-fold enrichment in uranium-234 and an initial absence of thorium-230. Then we can plug that into the matrix exponential. It will predict the number of atoms of uranium-238 and lead-206. We can naively plug that into our simple age equation, and we would estimate the age of this rock, which we know to be 5 million years, to be 8.8 million years. We've made a 3.8 million year error. This is not a detail, this is a big deal. So for old rocks, 5 million year old rocks, you can't undo the effect of disequilibrium because that disequilibrium has disappeared. For young rocks, however, we can undo it. If the rock hasn't completely moved back to secular equilibrium net, if there's some disequilibrium left in our rock, then we can flip the matrix exponential around, not producing a matrix logarithm, but an inverse matrix exponential. Looks very similar to the matrix exponential, it just has a negative sign here. And that allows us to take any present-day measured disequilibrium, relative amounts of these nuclides in the decay chain, and for any moment into the past, we can infer what the initial conditions would have been. It's the opposite of the matrix exponential. We could then use the forward and inverse matrix exponential to undo the effects of this equilibrium. And here's an example of that for a relatively young speleothem with an uncorrected uranium-238 led to a 6 age or date of 148,000 years. This speleothem is young enough that the disequilibrium hasn't completely disappeared. In fact, the 234-238 activity ratios measured today are 16% enriched in uranium-234, and the thorium-230 is enriched by 7% relative to secular equilibrium. We can then use the forward and backwards and inverse matrix exponentials to search a solution space and to find the age and the initial activity ratios that fit both the uranium-lead data, shown here, and these measurements for the activity ratios. And that gives us a corrected age of 161,000 years and inferred initial activity ratios enriched by 25% for uranium-234 and depleted by 34% with respect to for thorium-230. All right? Good. Everything that I've talked about so far was developed by other people, by Rutherford, by Albarede, by Noah McLean, and so forth. I implemented them into Isoplotter, but I didn't invent anything myself. Now we're getting to part 4 of my presentation, which finally reaches my contribution to this whole debate, which is in estimating the uncertainties of the disequilibrium correction. That uncertainty estimation is a tricky problem because the disequilibrium correction is strongly nonlinear, so a simple first-order Taylor approximation won't cut it. What people have done in the past is to use Monte Carlo methods to estimate the uncertainties associated with the disequilibrium correction. So I'll illustrate that with an example for a speleothem, Corchia speleothem, I think in Italy, with an uncorrected 238 age of 400,000 years and a present-day 234-238 activity ratio of 0.951, so actually depleted relative to secular equilibrium. Now we don't actually know what the present-day 234-238 activity ratio is. All we can do is estimate it by mass spectrometry within some analytical uncertainty. What the Monte Carlo method does, it takes a random guess from this distribution of measurements, and it then uses the inverse matrix exponential to find the best age and best initial activity ratios that fit that assumed present-day 234-238 activity ratio, and you repeat that multiple times, and you get a distribution, a collection of inferred ages, the mean of which is 580,000, and 2 times the standard deviations of which is 9,000 years. So that's giving us an uncertainty estimate for this particular sample. I decided to do things differently. I prefer to use a Bayesian approach to this problem, which doesn't take random numbers from the measurement distribution of the activity ratios, but from the initial activity ratios. Now, we don't know what the initial activity ratios were. We have to take a guess. And I'm going to make the naive assumption, I'm going to draw these random numbers from a uniform distribution between 0 and 20. I draw a random number, I use the forward matrix exponential to search the solution space, and I infer the corresponding age and initial activity ratios to which I can compare with my data to assign a likelihood to this particular value. I explore the entire space of parameters, and I get a so-called posterior distribution of ages and initial activity ratios, the mean of which is 580,000 years, and the 2.5 percentile and 97.5 percentile of which give us a 95% credible interval of 9,000 years, exactly the same as the Monte Carlo methods. So you might wonder, what's the point? Well, the point is that the Monte Carlo method works fine for young samples, but it breaks down for old samples. And here's an example for a speleothem from the cradle of humankind, the Hawklands basal speleothem flowstone, that has an uncorrected 238 age of 7.4 million years. This is a very old sample. Clearly, its present-day 234-238 activity ratio overlaps within uncertainty with secular equilibrium. If we do Monte Carlo estimates or draws from this distribution, any value below secular equilibrium will result in physically impossible solutions, negative ages. What do you do with those? Well, algorithms that were used in the past simply ignored those and worked with the physically possible solutions. That seems sensible, but it produces then a corrected age of 3.2 million years, less than half the uncorrected age, with a suspiciously small analytical uncertainty. The Bayesian method doesn't run into this problem. The forward matrix exponential never produces physically impossible results. Any sample from the prior distribution of activity ratios yields a physically possible outcome or likelihood, and my posterior distribution then looks like this. It has a peak at exactly the same location as the Monte Carlo method at 3.2 million years, but instead of having a very small uncertainty, it now has a very large uncertainty extending from 3 million years all the way to 8 million years. So we really can't say very much about the age of this sample. Now, to bring home this point that the Monte Carlo method can produce nonsensical results, to bring home that point a bit more strongly, let's push this real example to a semi-synthetic, more extreme scenario by just shifting the activity ratios exactly to secular equilibrium. Suppose that we've got the sample and it is exactly in secular equilibrium. There's absolutely no justification for making a disequilibrium correction, yet the Monte Carlo method will happily go along with it. Half of the Monte Carlo samples will be rejected, and we have this age of 3.3 million years, plus or minus 200,000 years, which is clearly wrong. The Bayesian method, again, doesn't have that problem. It shows us that all the sample can really tell us is that the speleothem was more than 3 million years old. It gives us a minimum age estimate, not really a maximum age estimate. Well, at least 8 million years may be possible, but we can't really say much about the age of this particular sample. Exploring this Bayesian methods some more allows us to show that really beyond 2 million years, if you suspect that strong disequilibrium might have occurred in your field area, the uranium-238 method really cannot be trusted anymore. And that's very annoying, because 2 million years is exactly the kind of age time periods, 2 to 3 million years, that we were interested in for human evolution. So what do we do? Do we throw our arms in the air and give up and just run with the cosmogenic nuclide dates? Well, fortunately not. There is another approach to uranium-lead dating that might come to the rescue. It uses this other isotope, long-lived isotopes of uranium, uranium-235. Uranium-235 is far less abundant than uranium-238, and therefore lead-207 is less abundant than lead-206, and therefore the uncertainties associated with this method are larger, but nevertheless it can be useful because the disequilibrium problems for lead-207 are far smaller than those for lead-206. Unlike uranium-238, which has two isotopes of concern, relatively long-lived isotopes that can cause problems, uranium-234 and thorium-230, uranium-235 only has one, protactinium-231, and that is easy to deal with, first because it has a much shorter half-life than both uranium-234 and thorium-230, so the correction is always going to be smaller, and unlike 234 uranium, which could either be enriched or depleted, protactinium-231 is always depleted. So the correction becomes smaller with increasing age, not larger. And you can show that very conveniently, actually. The lower precision of the 235 method is compensated by better accuracy at about 2 million years. At 2 million years, the 235 method, the benefits of the 235 method outweigh its disadvantages. To convince you that the 235 method is accurate, which is arguably more important than precise, I will show you three brief examples. The first applies to speleothems from Siberia. So there are two caves here, the Lenskaya and Botovskaya caves in Siberia, a place that is, like South Africa, characterized by quite strong disequilibrium of the uranium isotopes. The black circles and error bars show the uranium-238 ratios and activity ratios, and the blue symbols, error bars, are the uranium-235 dates. Circles are uncorrected, error bars are corrected for this equilibrium. You can see that the 235 ages agree very well with the 238 ages, but they are much more uncertain. The precision is worse, but the precision improves quite quickly with increasing age, and even though this particular section doesn't contain any speleothems older than 2 million years, it's not hard to imagine that beyond 2 million years, the 235 ages would have higher precision than the 238 ages. And there are speleothems in this part of the world that are older. So here's an example of that. It's from the Botovskaya cave. This is the 238 isochron, 2.6 million years. This is the 235 isochron, 1.6 million years, a 1 million year age difference. No activity ratios are measured for this speleothem. I would argue that this should not be trusted. You should rely on this particular isochron. In fact, when you consider the age difference between these two speleothems, you can actually infer what the initial 234-238 activity ratio would have been to explain this difference. That would be a value of about 5. Well, let's go back to the present day speleothems. Well, the inferred activity ratios for the Botovskaya cave are about 5. So that's a validation of the accuracy of the 235 isochron. Second example is not from Siberia, not from Africa, but from Israel, from the Ashkelon cave, in which Ash-15 was actually used to be a reference material for uranium-lead dating. Israel is a country with many carbonates that have been analyzed to death. There's a compilation of 904 speleothems in Israel that were analyzed for 234-238, and it shows that unlike Siberia and South Africa, caves in Israel in the Middle East are actually not far from this equilibrium. They are only slightly enriched in uranium-234. Because we've got this abundance of 234-238 activity ratios, we can actually replace this very naive uniform prior with an informative non-uniform prior using this prior information on the 234 activity ratios. And that then allows us to make a reliable disequilibrium correction beyond the 2 million year cutoff that I warned you against before. When we apply this correction to the Ashkelon data, we get a corrected age of 3.1 million years for the 238 method, which is in very good agreement with the 235 method. Again, giving us confidence that the 235 method is accurate. Now, unfortunately, the 235 method is no panacea. Here's an example again from Siberia, in which the 238 age is 4.9 million years. It is precise but inaccurate. The 235 age is 2.7, much younger, but yeah, maybe more accurate, but unusably imprecise. And that is because the uranium content of this speleothem was too low and there's not enough spread on the isochron. Unfortunately, this rock is not datable with the uranium-lead method. And that brings me to the final part of my presentation, in which I will go full circle, go back to Southern Africa, and revisit the speleothems of the cradle of humankind. Let's begin with the Hoogland basal speleothem, which I used as an example to show the benefits of the Bayesian uncertainty estimation method. Recall that the uncorrected 238 data 7.5 million years, using the tiny little bit of apparent disequilibrium measured in the speleothem today, that can be corrected to 3.3 million years, but with a very large uncertainty. Unfortunately, these measurements, which were measured by ICP-MS, did not include lead-208 measurements, which we need to do uranium-235 isochrons. And so we had to reanalyze these samples with a different type of mass spectrometer called thermal ionization mass spectrometry. I would like to take this moment to just say that in all the cases that we've studied so far, our mass spectrometer measurements, particularly for uranium-238 and lead-206, which we also get, are in excellent agreement with the published values. So the measurements made by Robin Pickering in Cape Town and in Melbourne, which are very difficult measurements to make, are actually very, very good. The only thing that we are doing here is propagating the uncertainties differently. Okay, so the data are good, but unfortunately we need the 235 method to gain the accuracy that we need to resolve the dispute between these different ages. And for that we are using thermal ionization mass spectrometry, which offers some advantages over ICP-MS. And so my colleague David Szymanowski from ETH Zurich analyzed essentially the same rocks that were measured by in the previous studies, samples currently provided to us by Tebogo, and we got the same uncorrected 238 ages, but we have a 235 age now, which is nicely between the 238 corrected and uncorrected ages at 5.3 million years. This is one of the most beautiful isochrons I've ever seen. It's a really reliable result, I would say. Second, Malapa, Australopithecus sediba, dated by the uranium-238 method in 2010. These are disequilibrium corrected dates, very high precision, a very good agreement between two labs at 2 million years. Again, thanks to Tebogo, we got access to samples from the same horizons that were dated back in 2010. We used the uranium-235 method and CAID TIMS. The isochrons are not as pretty as for Hoogland. The uncertainties are a bit bigger, but we still have good isochrons that increase the age of the speleothems, not by as much as for Hoogland, but by about 500,000 years. We can bracket the age of the fossil to between 2.5 and 3.4 million years with some uncertainties, which we will hopefully be able to improve in the future. And then finally, the town child was dated using a speleothem, a flowstone, that was collected at the top of the tufa deposit in which the fossil was found by my colleague Phil Hopley. We characterized this beautiful flowstone by laser ablation ICP-MS, showing quite high uranium concentrations and strong variability, very good conditions to do uranium lead dating. We targeted the high uranium layers to obtain a preliminary age by by laser ablation, giving us an uncorrected 238 age of about 3.2 million years. We then use a dental drill to subsample the speleothem and do TIMS, and that produced essentially the same 238 uncorrected age of 3.3 million years. The disequilibrium correction lowers that dramatically to 2 million years, but the 235 isochron, it's closer to the uncorrected age at about 3 million years, which we take to be a minimum age estimate for the town child because this was sampled above the fossil. And here's an overview of the work that we've embarked on in reanalyzing speleothems from the cradle of humankind. Again, we've got the potassium argon dates for East Africa, agreeing with the cosmogenic nuclide dates. The uncorrected 238 dates are also in good agreement with the cosmogenic nuclide dates, but the corrected dates are all much younger. Our preliminary minimum and maximum age estimates using the 235 method are raising these ages in the direction that implies that we may be able to resolve the difference, but it's still early days. We can't conclusively decide whether Australopithecus africanus and afarensis are the same age, but they might be. And I'll leave you with these conclusions, and I'll be very happy to answer any questions that you might have. Thank you.
All right, thank you very much, Peter. That was very interesting, for me at least, and I hope it was also interesting to the audience. And this is time where we can have questions for Peter. What would you like him to clarify? If no one asks questions, then I'm afraid Peter will have to ask you questions.
Well, maybe I can begin. I thought it's actually less of a geochronological question as a paleoanthropological question, that maybe some of the colleagues can answer. It comes from a geochemist and a geochronologist, so take it into account. But you compared East Africa with South Africa. Why do we have to make the assumption, maybe it's not an assumption, that the species living in East Africa should be of a similar age, or at least close to the species in Southern Africa? Could there not be 1 million years difference when those species lived? I recognize it's not a geochron question, but maybe
Definitely, you're definitely right. My understanding is that morphologically they look similar. But or maybe nobody's throwing stones at me yet. Oh yeah, Marion is shaking her head. I don't know, but that was, they are called Australopithecus. I don't know. I'm not an expert. They might be much younger. There's no reason why, yeah. Marion,
So, yes.
or Teboga.
Do our paleo people want to say anything?
The East African osteropods and the Southern African ones are morphologically somewhat different. I mean, you don't have to be an expert, you just look at them and you can see. They're all bipedal, but even their bipedality is variable. And their dentition is very specific to those species. So, trying to figure out what the connection is, we don't know yet.
Yes, and that's why I guess we need, because different is easy to tell which one is more, very dangerous word to use, but primitive, or, because that's what, I mean, when the town child was found, they said, that's clearly older than Homo erectus. So, is it?
And also, I think if we're presuming we're looking at Australopithecus africanus in Stackfontein, for example, there's a second or maybe even a third or even a fourth species hypothesis, because the town child's a baby, so it's really a bad example of what a holotype should be. So the only Australopithecus africanus we're certain about is the town child. The others might not actually be africanus, but there's varying opinions on that as well.
I shall retreat from this.
Yes. I want to throw in a geological perspective. I think some of the results we've shown, try to answer this important question of why has all or most of the geochronologic data from the cradle go to a narrow, time range in the cradle? Because the question has always been, why are we not seeing a lot of ages? I mean, are all these caves younger than 2.5 million years or 3 million years? Why are we not seeing speleothems that are 5? Granted, yes, most of the speleothems have been mined away, but there's still a lot of speleothems. Why are they not coming out at 5 million years, 6 million years, and so forth? Whereas for every corrected age, all the speleothems go towards 2 million, 2.5 million years.
And I think that's a geologic question, sort of in response to why we want to compare with East Africa. Because in East Africa, geologically, you look at the tooth layers, you see a wide range in terms of geologic ages. But you look at the speleothems or the speleothem ages in the cradle, they all converge to a narrow time limit. So it's not just about the fossils themselves, but the geologic materials also. Any other question or comment?
Well,
Yes, Scott.
I was just going to ask along those lines. I'm also speaking from not a very well-informed, position here. But is there something about the correction for initial disequilibrium could artificially be making everything look similar, like in time, in terms of the age?
Yes, actually, David Simonovsky recently brought to my attention the fact that the uranium-234, 238 activity ratios depend, it's a very difficult measurement to make, they also depend on the decay constant that you use, because you need to convert atomic ratios into activity ratios. And those decay constants have changed over time, and sometimes when you adjust the Hoogland speleothem in particular for the currently accepted value for the decay constant, instead of lowering the age, it increases the age. So there are systematic effects caused by just using the wrong decay constant, which may be pushing everything consistently in the wrong direction. So that's another complication to this whole story. And the beauty of the uranium-235 method is that it avoids that issue altogether. And so to Bogo's point, that's why this Hooglands basal flowstorm is important, because yes, previously no speleothems, or all the speleothems were relatively young, but we found, and you can trust this isochron, this is very, very beautiful isochron. This is a 5.3 million year old speleothem, so perhaps we may be able to find all the fossils somewhere in the cradle. Need to keep looking.
And one other thing was just, so it sounds like the 234 abundance is a purely physiochemical thing. It doesn't have to do with what's being eroded or what's being dissolved, like if it's a Archean granite or a limestone or a modern granite, it's all more modern physiochemical processes.
Yeah, yes and no. I think I'm not an expert in this, but certain kinds of soils can promote it, because just recoil and preferential leaching is not enough to get you to a 12-fold enrichment. But when the uranium-234 forms, it has a different oxidation state than uranium-238, and then chemical processes can separate them. Because normally, thorium and uranium are two different elements, they fractionate very easily. But uranium-238 and 230, they're both uranium. But if they have a different oxidation state, then they are chemically different, and that's a more powerful way to fractionate them. And then the conditions under which they were leached out of the rock do become important. Don't know if lithology has anything to do with it. Maybe it affects the kind of soils that you get. But yeah, that's what this paper from 1994 is about. How do you get a 12-fold enrichment? It's a very interesting problem, but it's real.
Thanks, Peter. Yes,
maybe a follow-up question, going back to the first point that everything sort of focuses in Stackfontein or in the cradle of humankind on 2 million years, roundabout. Is that from a landscape evolution perspective, is that something that one would expect, that at 2 million years you have an event in the landscape evolution that's forming flowstones, and then caves form around that, and that everything is 2 million years? Is that reasonable?
The corrected 238-206 dates are 2 million years. I would argue that they may be inaccurate. The ages may be different. Why they are all the same, yeah, harder to explain. But the 235 ages are harder to argue against. And so before we draw that conclusion, I think it would be useful to reanalyze these samples for 230 with the 235 method. Perhaps, it's early days, as I said, they may confirm the 238 dates. They may only be slightly different, but perhaps it completely changes the picture. It could do. Yeah.
All right, any other questions? Peter, now it's your turn to ask them a question.
Oh, is that a tradition here?
No. Well, everyone, thank you very much. Peter, thank you once more for a wonderful talk. If we could give Peter a round of applause. All right, thank you.